Hey everybody. So I used to focus like really heavily on this channel when in regards towards hyperbolic computing and everything around like hyperbolic geometry, but it's been a long time now since I've put out a video on the subject, and uh, the reason why I haven't put out like a lot of videos on the subject recently is because there's nowhere to go with it. To me, like essentially is the bottom line, right? So to me at this point, these things are researched, these things are known, and then it's just a matter of getting funding for them. I think that's like I've had like companies, people that are like in the startup space. Uh, they find out about hyperbolic computing, hyperbolic geometry, etc., and then there's overall about like 600 people in the world total, like flat out, that are in that space, and then so. Uh, there's very few people that know about it, that can talk about it, etc. And then so when they find those things, they reach out, right? And then like my flat out stance on it at this point is if anyone out there is in the hyperbolic computing space and you have funding, I will give you all of the research you could possibly imagine or want. I'll do whatever you want from a research capacity. I'll give you all of my research that I have, etc. But I have yet to run into anyone on the planet that can get funding around this. And then to me, it's so from a funding perspective, when you break this down academically, it's still in a lot of this is still in the realm of academic theory, not proven academically. But I can get you a PhD from any major institution in the world that can back up the theory behind these things, right? And like those people exist, and it exists within these communities. Like it's beyond theory at this point, but that's just how it is, right? And then the overarching math behind it all is less than 10 years old at this point, and that's like the bottom line within it that people don't understand, right? And then it's if you specialize in it on the mathematics angle, that doesn't mean that you have any understanding of it from the physics angle, and then that goes back and forth, right? And then there's that it's this is both a physics problem and a mathematics problem and a computer science problem. And then so it's like all of those rolled into one, and then so it makes it hard for people to conceptualize these things overall. But the mathematical concept behind this is like super straightforward, right? Like anyone can understand the mathematical concept behind it. Like I think like where people struggle is like why this actually makes a difference, and why it actually matters and how it matters in the real world, right? Because people are just like it blows, like people can't believe that this is actually like how the math works, and it's 100% how the math works. The math checks out. Again, like I can show you whatever experiment that you want around this. If you've been experimenting around with compression, deterministic outputs, etc., like whatever you want to prove within this space, like it's proven. I guarantee you, get funding around it, and we'll build a company around it. That's kind of the bottom line, right? But so the math behind it is super simple, right? So in Euclidean space, the circumference of a sphere is 2 times the radius of pi, right? And then that's just the very straightforward and known equation. Within hyperbolic space, the circumference of a Poincaré ball is 2 times pi, and then the sin times the sin radius of pi, right? And then so that's the big mathematical distinction. And then so what does this mean, this sin radius compared to 2 times the radius of pi? It's very simple to understand, like in actual terms, right? So this is a Poincare disk, and then so this is a ball that exists within hyperbolic space as opposed to Euclidean space. But then once we're representing it two-dimensionally, it's going to look very much like a sphere, right? And then so that's like I think a hard part for people to understand within that is like what the heck is the difference between this and a sphere? The difference between this and a sphere is how it operates, right? So you notice that everything is centered in the center of this sphere, right? And then so the center of this sphere is more dense than the outside of the sphere. And then so these outside, like the curve of this sphere, is an actual the curvature is in the space itself, right? The space itself is making this, we'll call it a circle that you're looking at, and then that's the difference, right? And that's the geometric difference to understand. Is it's like when you draw a circle in Euclidean space, it's a flat surface, and then you're taking that surface and then that infinitely flat surface, and then you're just drawing a circle within it, right? And the boundaries are those circle lines. Whereas within this Poincaré disk that we're looking at here, this hyperbolic ball, the edges of the space are what makes the circle. Like it's curved edges of the space overall, and then within that creates a unique physics inside of this ball, and then that physics is true even in digital space, right? And then so what is the physics difference between this and a normal ball? So again, as I mentioned, that the inside, the very center of this disk is more dense than the rest of it, right? And then think of it like layers. So then there's another layer that would go out here, and then another layer here, and then another layer here, right? And then outwards like that. Just think of there's like circles inside of this sphere, and then each circle is less and less dense overall. And then what does that mean? It means that as I'm going outwards in the circle, I can pack more and more data the more and outwards that I go. And then if I'm packing it like near the edges, like near these, like this actual boundary, I can pack infinite amounts of data because the line continues infinitely, right? That's what that mathematical equation does. That's what this does. It ends up doing, right? Is that you can never actually hit the boundary of this. And then so it creates a situation where if I'm packing data out here, I can pack like bajillions of times more data here than I can in the center. But if I start at the center and then I go out, I can stack data hierarchically naturally is the benefit over all of this, right? And then so overall, I'll get back to what we're looking at here as far as the code, and then I'll break this down to you and give you some code to walk away with. But the big thing that I want you to understand up front within this is hyperbolic computing versus standard computing. And then so why curved space changes everything. The big difference, the only difference to understand within this is that hyperbolic space is adding this curvature to the space, right? So imagine that you're trying to organize your entire family tree on a flat piece of paper. Your parents at the top, you and your siblings below, then your children, and then their children, right? Just like a typical tree, like a decision tree. It gets cramped fast, and then the paper runs out of space because families branch exponentially, and then so each generation doubles or more the number of people that you have compared to the previous generation. So now imagine that that paper could curve and expand as you move down the tree, creating more room naturally. And then so that's the difference between standard computing or flat and Euclidean geometry and hyperbolic computing or curved geometry. And then so this guide overall is to help you understand what matters within that. And then so starting off with the basics, what is Euclidean geometry? Euclidean geometry is the normal geometry that you learned in school. And then so all of these principles apply to it. You have flat surfaces, straight lines are the shortest path between 2 points, parallel lines never meet, and the angles of a triangle always add up to 180 degrees. And then so in computing, most AI and machine learning systems organize information in Euclidean space. Think of it like organizing books on flat shelves in rectangular warehouse. And then these are all facts of math that you learn in elementary school, right? And then these are just the facts of Euclidean geometry, and then you learn it as geometry, right? But there is a geometry that exists where these particular facts are not true, and that's hyperbolic geometry. And then so what is hyperbolic geometry? Hyperbolic geometry is curved, but not like a sphere. It curves outward. So that sphere that you're looking at, it's actually more like a saddle or like a Pringle chip. It just, when you're flattening it into 2D, it looks like a sphere. But it's like, think of it like saddle, Pringle chip, good example, right? And then so within this particular ball that we're looking at, space expands exponentially as you move from the center. Parallel lines diverge and they can spread apart. Triangles have angles that add up to less than 180 degrees, and you can fit infinitely more stuff in that finite area. So in computing, hyperbolic computing organizes information in this curved space. Think of it like having a warehouse where the walls magically expand the further that you walk from the entrance, and you can fit exponentially more shelves without the building getting bigger. And this is like the big area where everyone hits me up around hyperbolic computing, right? They're like, oh, we figured this out, and like we can get like 10,000x compression, and it's like, yes, 1,000,000%. You're not hallucinating. Like you can 1,000,000% do that. I can show you. I can demonstrate it to you. I can demonstrate it to you like that, right? I can demonstrate the reconstruction of it, etc. Exactly how it works. Find someone that has money willing to invest that can actually understand that concept, and I'll do business with you all day long. Like that's the bottom line of that, right? And then so part two, the key differences with just utilizing everyday analogies. So one is space efficiency, right? The crowded museum problem. And then so think of this scenario. You're creating a museum, you're curating a museum of human knowledge. And so you have every single topic within human knowledge that could exist: art, science, history, etc. And then each one of these branches into subtopics, right? History has like American history, world history, Eastern history, like ancient history, etc. Right? And then each one of these branches further into specific subjects from there. And then so the Euclidean approach, like the standard computing approach within this, is that you have a flat rectangular museum floor as the base, and then art section gets one corner, science gets another, etc. Right? And then as these topics branch, so Renaissance art is attached to Italian Renaissance, which is attached to Florentine school, which is attached to individual artists. You run out of floor space because you get like by the time you're having to get to individual artists. There's so many categories of individual artists, right, that you have like all of these lines that just go and it just gets like bigger and bigger, right? And then so you're forced to either make the museum huge, which is expensive and inefficient, or you have overlapping sections, which can be confusing, information gets mixed up, or you have to limit how many subtopics you can include so you lose detail. But within hyperbolic space, the museum floor curves outward as you walk, like a 3D image, like the images that will fool you, like. And then so the art section starts normal size at the center, and then as you walk towards the resonance art, the floor expands, and then so more room appears naturally, and that's just how it goes, right? And then so if you're the observer at the center of that disc, you can see the edge, right? And you'll see the edge as you're the observer, but as you walk closer and closer to the edge will move further and further away from your vantage point. And then so by the time that you reach specific artists, you have exponentially more space. Like you've had to walk exponentially towards the edge every single time that you get closer to the edge. And then the result is that you have infinite detail in finite area. It allows you to store more detail than you could in finite space because the space grows. It's like the different infinities, right? And then like understanding mathematically how there are different infinities, and then like how to actually run out of room in the infinity hotel, right? Like you have a hotel with infinite rooms and infinite guests, and then how do you get that infinity hotel to run out of room? And it's possible, right, mathematically, to make it run out of room within that. And then it's that same type of thing, but in reverse when you're talking within this, right? That basically that same equation, but in reverse, where you get more and more space added, the more stuff that you stuff within the space. And then so the real benefit of this is that hyperbolic computing can represent hierarchical structures like a corporate org chart, family trees, or knowledge taxonomies. And then it's not like 10 to 10,000x, right? 10,000x, no problem. Like more efficiently than Euclidean computing. And then I can give you and just go into more examples of this, right? Like a whole bunch of examples of it. And then, but other example, the concrete example, right? I'll just go over one here, would be Wikipedia. So the challenge would be that Wikipedia has 60 plus million articles with complex linking structures. Articles link to related articles, which link to more specialized articles. And then so the Euclidean limitation within this is that articles exist in flat embedding space. Related articles must be pulled close together artificially. General articles like science and special articles like quantum chromodynamics have to be encoded with the same number of dimensions. And then search and recommendation algorithms struggle with hierarchy. And then so within this, like it's you trying to encode and have a model go through like all of Wikipedia, or think of it like chess is the same type of thing, right? Like having a model go through every move. That's why you always have algorithms that trim the non-probable moves, right? Because you need that in order for because it's just that tree is just so big. Whereas within the hyperbolic solution, science sits relatively central. Then you have physics, which branches outward. Then you have particle physics, which is a branch from there. Quantum chromodynamics sits even further out. And then you have your specificity is the distance from the center, right? From the center of the Poincaré ball. And then search becomes a geometric function within that instance. So show me articles 3 steps more specific than physics. And then it's just doing a distance calculation from the center. And then so within that, you can fit the entire Wikipedia hierarchy in a hyperbolic space 10 times smaller than the Euclidean space, 10,000 times smaller than the Euclidean space. And then so the result is faster search, better recommendations, and less storage needed overall. Like here's a bunch more examples, right? Here's why I think that this matters is in terms of the future overall, but like stressing it overall like that. So I have yet to run into anyone that would actually fund this. And then like the reason it's the bottom line is that there's so few people in the world that can actually talk to you about these things, but it's the people that can talk to you about these things, it's literally like one PhD from every single institution that exists in the world, right? But they like and that's kind of how it is like in regards towards this. And then it's all of the theory is proven at this point, right? And I'll show you just one example within this video, but I could show you any other, like anything else that you want to do within this, I can show you examples of it, and I can introduce you to people that could talk your ear off all about the mathematics behind it. And so kind of common questions behind this, right? Like, so the first big common question is like, isn't this just like a mathematical trick, right? Like pulling a rabbit out of a hat? And so, no, it's more like discovering that you've been building houses on slanted ground without realizing it. Euclidean geometry is a choice, it's not a necessity. So for hierarchical, branching, or tree-like data, which describes most real-world information, hyperbolic space is the natural home. Using Euclidean space for these problems is like insisting on writing Chinese characters with the English alphabet. It's technically possible, but you're fighting against your own tools simply to do it. And then if hyperbolic computing is so good, why doesn't everybody do it? And there's 3 reasons, right? Historical inertia. We've built all of our tools, hardware, and training for Euclidean geometry. There's an extreme unfamiliarity with this, right? Most computer scientists and AI researchers aren't trained in hyperbolic geometry. Hyperbolic geometry as a subject overall is less than 10-year-old mathematics as the big umbrella of this, right? So you have to find someone that is a mathematician that focused specifically on geometry, that focused on geometry within the last 10 years and decided to go into hyperbolic geometry. There's not a lot out there, right? And then engineering challenges. It leads to, like, you have problems with numerical stability, which is big, right? Like, because it's numbers don't operate. That's the big thing, and the big thing that like mathematicians run into when they run into this, right? They'll do their standard distance calculations, and then they'll try to go through these things, and they'll be like, well, it's my distance calculations come out wonky. And it's like, well, yeah, dude, because it's a Poincaré ball, right? Like so, like if you're measuring your distance like here compared to here, it's 2 different measurements overall, right? And then that leads to significant engineering challenges. There's also problems with software libraries and hardware acceleration because it's all written for Euclidean geometry, right? And then so. Will hyperbolic computing replace standard computing? Like the bottom line within this, right? It's not a complete replacement because hyperbolic computing isn't better across the board. It's just light years better when it comes to certain problems for AI. And then so it's not better for everything, just for problems with natural hierarchy, branching, or tree structure. So think of it like Euclidean computing is great for grids, symmetry, uniform relationships, like images, regular patterns, physics simulations, like everything that we've used computers for the last like 100 years, right? Hyperbolic computing is great for hierarchies, networks, decision trees, language reasoning, planning, and knowledge graphs, everything that we've been utilizing computers for the last 5 years. And then so the future uses both, right? And then it's just understanding which geometry that you need to utilize for which particular problem. And then so in conclusion, the geometry of intelligence. So the space that you choose shapes what you can easily represent. And that's the bottom line within it, right? Flat space naturally represents uniform, regular, symmetric structures, whereas curved space naturally represents hierarchical, branching, exponentially growing structures. Most real-world knowledge, like language, reasoning, planning, social structures, biological taxonomies, these are all hierarchical and branching. All of these would be better in hyperbolic space. And then so we've been forcing it into Euclidean space because that's what we know how to do and what computers are based off of, right? But hyperbolic computing isn't just faster, it isn't just more efficient. It's a fundamental alignment between the structure of the problem and the structure of the solution space. It's like finally discovering that fish are better suited to swimming than to walking, right? As we build AI systems that need to reason, plan, understand context, and navigate uncertainty, the question isn't whether we'll use hyperbolic computing, it's how quickly we can make the transition. And then so there's two, like the biggest, like everyone will point out, and I have a ton of it, you can go through the back channel of my videos on this channel with regards towards hyperbolic computing and compression. That's not what I want to show you today, right? I want to show you something different that you would utilize as a real world use case today. Like, why would someone actually want to invest in this if they actually understood it, right? Which is like the big problem. The reason why is that you could take any existing technology around AI that currently exists and make it better if you actually understand the math behind these things. And then so what I'm going to demonstrate and showcase to you here is hyperbolic chain of thought reasoning, right? So this is utilizing standard chain of thought reasoning, but I'm utilizing it within hyperbolic space. And then so I'm creating hyperbolic embeddings for the reasoning space, in this instance a Poincaré ball. And then I'm having the model utilize geodesic navigation through the reasoning space, which creates hierarchical reasoning tree structures, and then a comparison of that with the standard Euclidean chain of thought. And then so what we have here at the end is essentially the generated outputs, right? And then so I give the model 3 problems, and then so in this first problem I say, if a train travels at 60 miles per hour for 2 hours, then increases speed to 80 miles per hour for 3 hours, what's the total distance traveled? And then it goes through its reasoning steps, and then because of this reasoning in hyperbolic space, it comes out with a much more clean solution, and we get therefore the answer is 360 miles, right? And it does all of this step-by-step math, all the problems that people associate with, like, these models are dumb, they can't understand math, right? Because you're trying to make them do math in Euclidean space when their environment is hyperbolic space. And then so if you just allow them to reason in that, it's going to make more sense, right? It's not going to make more sense for your calculations, because your calculation is going to be off because of all of the physics that are associated with hyperbolic space, but to the model it makes beautiful and perfect sense, right? And then so that's what they go through. And then so this same problem number 2, a baker makes 12 cupcakes per batch. If she makes 5 batches and sells 3/4 of them, how many cupcakes does she have left? This is a 270 million parameter model, by the way, right? And then we come down here, and then here's all the logic, right? So 15 cupcakes left, and it goes through all the steps, 4-step process that it goes through and reasons through to come out with the exact equation within that, right? Again, like, models suck at math, right? No, it's that humans suck at math and putting the models in the wrong environment for them. Like, it's like you train the model on like multiplication and division, and then you give it like addition and subtraction. You're like, this model sucks. Like, well, yeah, you trained it on the wrong stuff, dude. And then so like here's problem 3. If x plus 5 equals 12 and y equals 2x, what's the value of y? Same thing, same process, right? Models suck at this stuff. No, they don't, right? It's just x equals 7 and then y equals 14. Boom, there you go. And it's able to solve and reason through that just exactly as a human would within that process and that output, at least. And that's the result, right? Whether or not there's actual reasoning there or that's just the output, I'll leave that up to you. But so the output is the same. Only thing is that like you're testing these models in the wrong geometric space and then wondering why they're not working. Here it is. And then so lots of different stuff you can do within that too, right? Compression, like etc. Like things that might seem like magic. It's like you're just utilizing the wrong geometry, literally this, right? And it's understanding this, that like the difference between this equation and this equation is literally like all the difference in the world, right? This math compared to this math. And that's what, like, I can't explain this enough, right? That, like, it's all of the power. Like, if you, then that's the part of this that people don't understand, right? So, like, if you throw a bajillion, trillion, trillion Googleplex dollars behind this, and then I just do this, I win. Like, it doesn't matter how much money you're putting into this, right? Because you're always going to be like inhibited by this. Whereas all I need to do is just get around this. So, like, it's like money doesn't mean jack in this equation, which like people don't get that, right? It's just like, do you understand this compared to this? If you don't, then all of your money is going towards this, and you're just lighting it on fire. Whereas if I put $1 towards this, it's going to be your $1 trillion towards this. Like it's just that simple, right? Overall. And then so I'll leave a link to all of this. Hopefully this gives you a better understanding of hyperbolic geometry overall. If you're one of those people that, like, you've run into these things, you're like a mathematician, like you're computing these things, you come out with like crazy stuff that you can do with this stuff. You wouldn't be the first person that's contacted me or reached out to me on that. And on that, you're not crazy at all. And then, yeah, you're 100% right. If you can get money and funding behind it, then talk to me about it. If not, I'm kind of over all of this at this point until actually someone that can actually understand it, that has money, is one to back this space. But so I'll have a link to all of this. If you like this type of content, please like and subscribe. Thank you very much.